So we'll say a few words about model predictive controls, and we'll discuss also about some of the tricks and the practical hurdles that come when we have to program the model predictive control. And then we'll look at what is really interesting and what, if we want to be extremely robust, which is called scenario-based model predictive control. Model predictive control is a form of control that uses optimization. Like, not surprisingly, we do a lot in this part of the course. So the goal is to obtain a policy. Remember, what's the difference between a policy and an action? That's the language of optimal control. An action is, for example, a set point for the generator. That's a decision you take. A policy is not a specific action. It's a set of rules that says, if in the future I see this and that, here is the action that this rule will force me to take. So a policy is a rule. And as we have seen last week, sometimes it's better to have policies than actions. In particular, if there's some uncertainty. We saw last week on the microgrid that if we wanted to find a set point of all the generators that is able to control correctly the microgrid, there was no set point for a region of uncertainty. There was no set point that was able to satisfy all the constraints, but the policy was able to satisfy all the constraints. So that's the difference between policy and action. Now, this technique that we'll use, that's very fancy and very simple, finds a policy that is not written explicitly. So we will not write a rule like we did last week. Last week we said, for example, G2 is U, the sum of the disturbance plus V, and the problem was to compute the parameters U and V. So we had an explicit form of the control. Here we will not try to have that. The rule will emerge as the result of a computation. As we will see in a few more minutes. It requires to have a state model. A state model is something of this nature. Given the state of the system, so the state of the system is all the variables that play a role. It's not just the electrical state when we have electrical grid, but it may be all the variables that play a role in the problem and that are not control or disturbance. So we observe the state at time t, directly or indirectly, and we choose one control action. Like last week, nature will play after us a disturbance. And as a result of our action and the disturbance, the state becomes something else, which is the same thing we've seen last week, except now we have time added to the variables. The next state is a function of the current state, the control decision we took, and the disturbance that came after. So it's important to remember that in this mental model, things happen in this order. First, we observe the state, then we choose a control action, and later, against us or with us, we don't know, the non-coordinated with us, the disturbance will be played. Of course, we need to attribute a cost to that because we're using an optimization framework. So we assume that there is a cost associated with the action that we took and the state that our action plus the disturbance led to. So that's the new state, that's our action, and we pay for this. We pay for what we do. That's typically a cost because by doing a certain action, we may need to use some resources that have a cost. And as a result of our actions, it's like everything in life, the results of our actions is a new set of things, and we need to pay for this new set of things. For example, if we're in a grid, the new set of things might be the voltage, and the cost might be a soft penalty for voltage. That's an example. That's the framework, and the goal is to minimize not just one step, but the integral of this over some periods of time. So let's see an example, perhaps the simplest example. Model predictive control, as we will see, has the ability to look ahead. Because of that, it is very often used when there is some storage in the system. So where the effects of what we're doing now will have a long-term consequence because there is some storage. There is some storage in the BSS, in the battery system of the labs that you're playing with. Here, that's another form of storage, a thermal storage. That's the simplest example of how you control a house if you have a modern heating system of today. So the goal is to manage space heating with a heat pump. when the prices of electricity are variable. So if the prices are not variable, probably you don't need an MPC, but if the prices are variables, you have questions like, if the electricity is very cheap now, presumably because there is a lot of excess electricity in the grid, then you want to heat your house perhaps a little more, because a house is, even if it's not perfectly insulated, is a thermal battery. It has a capability to store the heat in the walls, in the building, in everything, if the windows are not large open. So if your house is at a temperature of 21 degrees and you stop heating, then the temperature will be perhaps 20 degrees 1 hour after, without heating at all. That means during 1 hour, you were relying on the heat that is stored in the building itself. Of course, it's not a storage like pump storage, that you will be able to use over long periods of times, like days or weeks, but it has some inertia that we would like to capitalize. To do this, you need a house model, and that's very easy to do. There is an excellent book that I take advantage of making a small advertisement to it. David McKay, the book was written in 2008. It's freely available online, and it's called Renewable Energy Without the Hot Air. It is a set of David McKay, unfortunately passed away a few years ago. He was a physicist who was interested in information theory and the energy problem. And this book contains all the physical model, all the numbers you need to do that kind of renewable energy control. For example, it has all the models for a house. So I took this model from his book, and we have a model of this type that says that if I, at a given time t, if I inject into the house some amount of electricity, of energy, for example, I have a heating system, what I inject is not just U of t, but is U of t multiplied by the coefficient of efficiency. If you have a resistive system, which is not recommended, that's the cheapest and less efficient way of heating a house, the coefficient of efficiency is close to 100%. That means when you heat, when you dissipate energy through a resistance, practically all the energy goes into heat. That's in fact the inevitable end of energy everywhere. But if we use a heat pump, the coefficient of efficiency would be larger. If it's a heat pump that has a very good secondary circuit, it might be 2 to 3. So as you know, a heat pump works by exchanging energy from another part of the environment and multiplies the electricity by having a coefficient of efficiency of 2 or 3. So that's what you put into the house. And what you put into the house goes into 2 places. Part of it goes away because a window is open, for example, or even if a window is not open. So this is a winter example. If we would have a summer example, it would be the other way around. That's winter in Cambridge, UK. When you heat the house, the part of the energy you put into the house simply goes out. And physicists tell us a simple model is that per time unit, it's linear proportional to the temperature difference. This is a crude model where the outside temperature is given here and the inside temperature is given there. So capital T is the inside temperature, theta is the outside temperature. I say it's a crude model because this is as if there would be only a completely homogeneous house and a homogeneous outside temperature, which in reality is not the case. It might be colder on the north side than on the south side. If it's during the day, there might be more wind on one side. So a full-fledged model would need to account for this. And this is what is done in sophisticated building controls, like the building controls you can have in buildings like at EPFL, in the modern IGM building, for example, does that kind of thing. Then you need to model the solar irradiation and also the temperature inside the house is not a single temperature. There might be different temperatures at different places. So it's a bit more complicated. Typically, you have a sum of a number of things like this. But for a small house, that's probably good enough. So that it captures how much temperature is lost. The key coefficient is the leakiness and depends on how well your house is insulated. This is what you play with. And then there is a storage component, which is given by the inertia of the building. Part of this energy, hopefully the largest part, is used to increase the temperature. That's the goal. When you heat, the goal is to increase the temperature. not to leak it out. But by how fast you increase the temperature depends on the inertia of the building. If you have a big stone house, it takes a huge amount of time to heat the stones. So the capital C here will have a very large value. And those are two independent quantities that reflect the quality of a house. You can have a house with large inertia and very large leakiness. That's typical of old stone house. It takes a very large time to heat them, but they leak also a lot, so that's fairly bad. Modern house would tend to have a very small leakiness, and the inertia depends on the construction. If it's brick and stone or wood, the inertia will be a bit different. So in this book, we have the parameters of this house, which was David Mackay's house in Cambridge. So I put them into the model. Of course, this was a partial differential equation that perhaps we would like to solve if we are simulating what happens in a very high temperature, very fast flow system. But that's not the case here. We're talking of thermal system at the temperature where we live. So the thermal exchanges are very slow. We're talking of minutes. So here that can be very simply replaced by a discrete time model, where I write exactly the same thing here. I replace the derivatives by the differences, discrete time differences, and we find a similar thing here, where I take delta t in this example of 1 minute. So if I massage a little this formula, I obtain this. The temperature at time t plus 1 is equal to some coefficient times the temperature at time t, plus something that depends on U, the amount of energy I've put, and something that depends on the outside temperature. So that is my model of the house. We see that it fits that's the model I needed to apply model predictive control. I have the next state here. So now the state of the system is the temperature, the inside room temperature. The next state is equal to a function of the previous state of the control action and of the disturbance here. The cost, that's part of the modeling to decide on the cost. We will see various options. But here I combine two things. I combine first monetary cost. That's my primary concern here. As a owner or manager of this house, I want to minimize the energy cost. And essentially, I want to take advantage of the low cost periods. Plus a penalty that accounts for the comfort. That's a way of what we call a soft constraint. We could put the constraints into the problem, or we could put them in a soft constraint in form of the penalty. Both have their pros and cons. When we do robust things, it is usually simpler to put soft constraints if the thing is not a hard constraint, which is the case here. I want, for example, the temperature to be between 19 and 21 degrees C. If there is a short period of time where I hit not 19, but 18.9, probably that's good enough. So it is really a soft constraint. So that's what I do here. I put a function, which is this one here, a penalty of 0 when we are within the dead band, and a penalty that has this increasing or decreasing function when we are outside the dead band here. So that is the system. So this constraint will essentially signal to the system, whenever I'm here, I'm fine. You should try to not be very much outside here because you'll pay a price, and this price here, we can take it large enough. Now, how does MPC work? So given this framework, we observe the current state, for example, the temperature. We need to obtain a prediction of the disturbance. So that's the first important thing about MPC. MPC looks ahead in the future, so it takes a prediction. As we will see, this prediction doesn't need to be extremely accurate, but you need a prediction of the disturbance in the future. Then we solve a multi-time step optimization problem, a bit like you did in the dispatch plan, where we dispatch the energy, UT, over some horizon. And the horizon is the number of time steps in the future. It should be large enough to incorporate the variation that we're interested in. For example, here you want a horizon that's at least 1 full day. because there will be an alternance of day and night, low cost and high cost periods. So you want to look ahead large enough in the future. Then you optimize over all the actions you need to take, assuming the prediction would be the true future. So you decide of a trajectory of the future, but you implement only the next step. You implement the next time t thing you want to do. Then at time after you've taken your action, so you wait. If the time step is 1 minute, you do this. Then during 1 minute, what will happen? Well, there will be a disturbance. The disturbance is due to the fact that the outside temperature is not exactly what you had predicted, but also that your model is not an exact 100% exact model. The inside room temperature will not be exactly what you have predicted by your model, even if everything you could measure is obtained with 100% accuracy. For lots of reasons, but that's a fundamental thing. A model is only a model. It's never 100% accurate. For example, the model of your house will not account for, as I said, the fact that the temperature is not the same everywhere. The wind may play a role and is not in the model. Or stupid thing, somebody opened the door and then that caused more leakiness than in the model. So the leakiness probably captures the average door, the effect of average in and out and door opening, etc., but perhaps not at the time scale of a minute. So when that happens, you measure, you wait for 1 minute, then you measure again the next state and you do it again. I will give an illustration here in another use of model predictive control that's not in the scope of this course, but is easier to visualize. This is used also for autonomous car driving. So if you drive an autonomous car, or if we as human beings, we drive, we do essentially the following things. So we observe where we are. So here I'm observing the position, probably also the speed and the rotation of the wheels, everything. And I know where I want to go. That's my prediction of how the road will be in the future. I obtained this by camera, by reading the road. So I know here I want to turn right here. So based on this, I will compute an optimal trajectory at time t based on where I am. And this is the optimal trajectory that I think will be done. However, I implement only the next action. The next action, which is, for example, the steering wheel action, leads me here on this trajectory. But for some reason, the true place and speed where I have at the next time step will be a bit different. For the same reason as we said before, my model of the car might be a bit inaccurate. The road might have some roughness that I had not modeled, etc. So I will be here, not where I had predicted. Hopefully, I'm not too far away. And then I will do it again. From this point, I will compute another trajectory. So we see this balance between two things. We look ahead, and here it is the fact that we look ahead that was saying, I want to turn right. I was not just looking at the next step where I want to go, like we did in some other forms of optimization. If I say I want to go here, for example, if I see only this part of the road, then I would decide I want to go here. But no, I know it's turning right, so I want to optimize my trajectory by going towards the chord of this bend. So that's the first thing. We look ahead, and the decision we take now is based on an anticipation of the whole future. But we don't blindly follow what our look ahead was saying. We redo it again by adapting to the result of uncertainty that is deployed after a decision. So that's what MPC does. And we do it again and again. That's why we also call it a receding horizon. Receding horizon means the horizon keeps moving as we move. So we're not planning for a specific time interval like we were doing, for example, in the multi-time step dispatch plan, where we are Swissgrid, we really want to do the dispatch plan of tomorrow. So the horizon is well fixed. Here, the horizon is just a technical means to take the good decision, but is not a fixed thing. It will continue moving on. So let's do this for this house here. We have to control the over horizon H here. We have to control the power set points of the heat pump every minute, for example, which is already high speed for a heat pump. We want to minimize over the horizon the monetary cost, which is this, plus the penalty cost of the temperature that we will have as a result of our action. And the temperature is given by this equation. The temperature at the next that results in my action is given by this equation that we see is linear and is a combination of our decision here, of the previous state, and of the outside temperature, which is now assumed to be known from a forecast here. So that's an optimization problem where the things we're interested in is U, all the values of U. T are existing as optimization variables. We're choosing them indirectly because by choosing U at every time step, we force the value of T. But the value of T we choose are the value in the future. The current temperature is measured, remember, when we start at time T, we measure capital T at time T. And the variables that we optimize are the future temperature. Again, we don't optimize by choosing them, because they follow this equation, but they are part of the optimization variables here. So that's what we do. So I'm just repeating here. And the key thing is that we implement U of T only. We implement only the first. We complete this entire trajectory, but we implement only the next step. So this is what I implemented here in MATLAB. I'm showing 2 days. The horizon is 1 day and the simulation is over 2 days. On this right axis, on y-axis on the right, you have the prices of electricity. So you see that the prices are low during night, probably because there's a lot of continuous generators, nuclear probably, that continue to run at night when there is not much use of it. Is high at the morning peak, is medium value when the day starts, probably because now you have solar energy that's starting to kick in here. Is even lower at this period here, which might be because that's the peak of the day, and that's a day, for example, in March or April, where there is sunshine. So we have the lower price here, and then the medium price here, and the peak price here. And again, that continues here. So I assume the price is unknown, they're given here. I also assume I have a forecast of the outside temperature, which is given by this very smooth function. So that's an example of an extremely crude forecast. That might be a forecast based on historical time series, which is of course not very accurate. That's just taking the season averages. You might have better forecasts, and as I mentioned already, in the context of renewable energy, weather forecasts are now available and are parts of the renewable energy technology. Here I took the very simple one. And in dotted line is the actual realization of the outside temperature with some variations, as you can expect. Now we see here the room temperature on which we can indirectly read the actions we took. So we see that here the penalties were set between 19 and 21. And we see that we never violate the penalties because the cost we put on violating the penalty was probably large enough. And we see that the room temperature, now that's a simplified case where I don't care about the temperature at night and day. Probably during night you want a lower temperature. That would make the exercise a bit more complicated, but assume because David Mackay was working very hard and had conf calls at night over Zoom and so on, wanted same temperature all day and all night. So that's the band. This band is essentially, the existence of a band is giving the possibility to store energy. And we see that happening here. We see that there is a peak here at this in the early morning, and we see that the MPC has anticipated the peak. When we see the slope here, the temperature increases. That means we're heating the house. So here we're heating the house. Here we're probably heating also, but just enough to maintain the lowest temperature. When we don't heat, the temperature drops according to an exponential, a negative exponential here. So we see 3 phases. Here we heat at some value that's just enough to maintain the lower bound. Here we heat at the max, and here we stop heating. So U is 0, and that gives us this heat. And now we see that we start heating again. And why do we heat again? Because the price is low. And then we stop heating, and then we heat again. Here we are forced to heat again. No, here we heat again because we anticipate a period where the price will be high. It would have been better if we could have heated more during this period where it's very low, but probably the storage, the leakiness is too high. You could not do it, or the here we were not able to go high enough. So this is the result here. So this two-source behavior is showing exactly how we take advantage of the low cost here to heat at maximum the house, and we do it at the latest necessary point. We just heat the max temperature just when the price gets at the highest here. And we see a similar pattern on the following day with different values because the outside temperature is a bit different. So we see also that the duration, the periods at which we do it, they're qualitatively the same, but they are different. So the MPC has adapted to the fact that the outside temperature is different. It's not just taking the forecast, it adapts, it takes the forecast to compute a trajectory, it implements the first step of the trajectory, but for the remaining steps, it will adapt by remeasuring the state here. So that is how this MPC works, and this is, I would say, the state of the art today to adapt to renewable energy. Here we have variable energy costs. We'll talk a bit more about that next week, but that's a way to signal to the users behavior that hopefully would lead to optimal behavior for the entire grid. The optimal behavior is essentially that there is not energy available at the same price at every moment of the day. And here we incentivize the users to make use. For example, we see that we heat here at a period when there's a lot of sun, we heat more, whereas if I had, that's the counter example, if we use standard technology, which essentially there's thermostat. Here the thermostat is optimistic, so we put it at 19 degrees. If we put it at a 20 temperature, it would even be worse here. The thermostat will do something like this, right? It keeps the temperature around almost constant. Of course, it cannot keep it constant because the only thing it does is on and off. So it will heat, then stop heating, then heat, etc. So when the outside temperature is low, we see the heat period become smaller. This is what the thermostat would do. And here the monetary cost of this exercise, as you can see, is much larger than as this one. So there's benefit for the user. And also the goal of this, if the system is set right, if it's set in order to optimize the global grid, it's not just optimize the profit. It gives also the signal, because we see here that we're heating practically always, regardless of the price, which means we heat also at the periods of the day when energy is very expensive and where energy might be a problem, in fact. In the coming years, we know in Western Europe, we might have electricity deficit problems, so that could be controlled by mechanisms like MPC. Question?
At the scale of EPFL, since we have a lot of EV batteries, etc., do we use MPC?
So at the scale of EPFL, we have a completely centralized heating system with a big system that has just been changed 1 year ago. So I'm not sure about the new system. The old system, yes, was using a gas turbine, which is controlled by some crude looking ahead system. What happens with the new one, I'm not sure, but perhaps you could inquire and tell me. But certainly every new, I would guess yes, to be verified, but I would guess yes. So any new deployment of an energy system will use that kind of technology. That's really the absolutely standard technology. And you will see in the lab that we can do it also, and this is done for controlling microgrids or grids where there are voltage problems, where we store energy in a battery instead of storing it in a house. So the equations are very similar. Yes?
And have we looked into the impact of such algorithms in terms of, because it's super intensive compared to just a controller or stuff.
So the question is, how about the computational cost? Yes, it is, as you will see in the lab, it is computationally intensive in the sense you have a whole lab and equations to write, and we will discuss in a few more minutes all the tricks to avoid doing things wrong in how you write the equation. Here still we're talking of time scale of minutes, right? So we do one computation that needs to be applied for the next minutes. So I would not call this compute intensive, except if you want to measure everything everywhere, yes, it will be compute intensive. Also, and that's why we will see a number of techniques, these techniques practically work well when you have a lot of linearity everywhere. So you will try to linearize everything. So this example that I gave is extremely simple. Of course, the dimension is simple, but the model is linear here, like we see. So this is a big linear program. So linear programs are technology that are deployed everywhere, and you don't need a big computer. You need typically something in the cloud that will do it for you. If you're interested, those are the parameters of the example. They come from David McKay's book. So, and the penalty that I took here was very large. So it's 1 franc per degree C of violation per minute. So if I'm saying the optimizer, you're allowed to violate the temperature deadband, but the penalty is 1 franc if you violate during 1 minute. And you see that the overall cost over 24 hours is, or over 2 days, is a few francs. So of course, the MPC will try very hard to not pay this. And this is exactly what happens. So the hard constraint is in fact implemented. Voilà, so that's our first pass on MPC. Now, when we do MPC in practice, related to your question, we want to make it as simple as possible. And also, we are very often confronted with similar problems as we had last week, but worse, because now we have a multi-step problem. So what we will see in the second part of the lecture is how to transform many non-linearities of mean and max by and avoiding the pitfalls that are easy to fall into. For that, we will review a few facts about mean and max that are part of any course on optimization. So let's see that, perhaps in the form of a quiz to get started. Here, I'm looking at 2 quantities. There's a function of 2 variables, x and y, where x and y have some constraints, but the constraints are independent. That means y lives in a set here, x in another set. I maximize over y and I minimize over x. You can easily imagine that we will see things like this. For example, when we have a penalty cost, we're interested in the worst case cost, we will have a max somewhere. And then we minimize everything, so we take the mean. And I'm asking the question here, does it matter if I change the order, if I minimize first or if I maximize first? What's your guess? I close in a few seconds. Closing. The majority says hi, but says A, but we have a tie, and the correct answer is C. And let's see a mnemotechnic way of remembering this. Imagine X is the dimension of the chessboard, Y is the other dimension, and imagine as a thought experiment, or it's a very big chessboard, otherwise, you put mice and elephants on the same chessboards. Not a good idea because elephants are afraid of mice, but assume you do this. And you have elephants that are small or large, and mice that are small or large. But a small elephant is always larger than a large mouse. Okay. First thing to remember. Second thing, assume there's enough of everything everywhere, so that on every row and every column, there's always at least 1 mouse and at least 1 elephant. Now let's look at our formula. F is the weight of the mass of the animal that is on this chessboard. So if I compute max over y of x of xy, so xy is a coordinate. If I am at coordinate xy on the chessboard, there is a certain mass here. and I take the max over y. That means I scan all the y-axis. I fix some x, so I'm here, for example, for x equal 2. I scan the y-axis, and I obtain what is the max. So this, when I do this, I first take the max here over this column. And then I take the min over there. So once having done that, I look at every index of every column, and I take the min. What do I obtain? When I take the max, I always obtain an elephant. Right? On every column, there's at least one elephant. There are small and large elephants. There are small and large mice. But the largest animal is always an elephant. So I always obtain an elephant, and I take the min. So I take the min of all the elephants that happen to be the largest on each of the rows. So it's probably this one that you want here. So that obtains an elephant, and you take the smallest of the elephants. When you change the order, what do? Now I do the same game, but opposite. I fix y, for example, here. I take the min. The min is the smallest mouse. And then I take the max of what I had over all the rows. So that's always a mouse. So the max of the min is the smallest mouse that was elected here. And here the mean of the max is, sorry, the largest mouse that was elected here. The mean of the max is the smallest elephant, but an elephant is always larger than a mouse. So this is larger than that one. A star is larger than B star. This is true in general, even if we don't have mice and elephants, even if the constraints I put are not true. But that's a mnemotechnic mechanism to remember this. This will always be true because an elephant is always larger than a mouse. It has a name. It's called the max-min inequality. And in fact, it's related. Oh, I had a nice animation here. Okay, so we see here the max-min, which is this mouse, which is a large mouse, and the min-max, which is a small elephant, but it's still there. It's related to saddle points and duality. In fact, when we compute the dual value of an optimization problem, we find the solution of the dual optimization problem. The dual optimization problem, if you remember, that was obtained by, for lambda and nu, the function to be maximized is the optimal value of the unconstrained problem, the Lagrangian here. So we can write this in the form. We take the max over the Lagrange multiplier of the min over the optimization variable of the Lagrangian. Now it can easily be seen that this is, if we invert the two, when we take the max over the Lagrangian of this, in fact, we obtain exactly the objective function. And so with the constraints, and so the min here will give us the value of the primal problem. I say it's easy, it would require some more explanation, but I don't give it here. So min max is at the heart also of duality, and weak duality means that the max of the min is always less than or equal to the mean of the max. So this is exactly what is called weak duality here. So the dual, the first statement on duality is another instance of what we see here in another form. And we know that sometimes it's true, but when it's true, it requires things. Typically, the problem is convex, and we have constraint qualification. For example, everything is linear. So this is not always true. The same happens for this inequality, A star and B star. Generally, there's not equality. It may happen that this is true. For a mouse and an elephant case, it will not happen. But if you assume there can be mice that are as large as an elephant, then this could happen. Voilà, so that was the first thing to remember. Second thing now, I do almost the same, but I first minimize, then over y, then I minimize over x. And then I change the order. Can we say also something in this case or not? close the poll in a few seconds. And here your intuition is perfectly right. So the majority says B, which is the correct thing here. So as long as we keep the same operator, mean and mean, then there is no problem. It is sometimes called the associativity of mean. Essentially, we can say that the mean of the mean can be expressed also as the global mean, if I consider as a variable the joint variable, with a constraint that's the combination of all the constraints here, then we see that it's the same, and very much like how you compute an integral. If you have a double integral with respect to two integration variables, you can fix x, then look at what is the space of y, integrate over this, and then integrate over y, or the other way around. This works. So the same is true for mean and, of course, for max here. So take-home message, we can mix and match means. Yes, we can mix and match maxes here. But as we have seen, be careful if we have a combination of mean and max here. The combination plays, the order of the combination plays a role, but not if it's the same. So let's apply all this to this further quiz here. Here I'm showing problem P1, which is this one here, which is one of the many variants of the problem we're interested in this morning. And I'm developing the problem P1 to make it, because I have my function phi, which is nonlinear. I want to get rid of it. I propose two ways of getting rid of it. Which one, if any, is a correct one? I close the poll. So the majority says B, which is incorrect. The correct answer is A. So that shows the importance of doing those drills. It's very easy to do one for the other. Very often when we read a paper or a software, the thing is presented in this form. And what we should be able to do is to know what this is representing, because this is the modeling. This is a thing we can discuss. You can discuss with your customers, with the rest of the development team. Does this make sense? Discussing this is more difficult. So what are we doing here? When we minimize the total cost, what is the total cost? Is the cost of energy plus the max of the penalty. So we minimize the cost that we consider over horizon is the integral of the energy and the worst case penalty, which is one way to do, not necessarily the way we want, but that's one way to do. And it means we will try to put a penalty for the worst case penalty, which means if you violate the temperature deadband 10 times or once, it would be the same penalty. If you violate 10 times by the same amount or once, it will be the same penalty. The max does not integrate here. That's what this is doing. Now, if we do this, then that gives us exactly that. That's the max removal function we've seen before. Let's explain why. If we put it in all details, this is the objective of the problem P1. The max, the sum, the integral of the cost, plus the max of the penalty term. The penalty term, this type of function, we're used to that already, that can be expressed as a max of linear function. In fact, any convex piecewise linear function is a max of linear functions. This is how we can translate and in fact approximate any convex function by something that will have a finite number of linear components. So it's the max of this max here, which I can write in this form. I give a name to each of those. I call it LIS. So L1S is this one, L2S is that one, L3S is this one, which is 0. We recognize here a max of max. Now, because we know max is associative, we can change the order. So it's the same as the global max. So it's the max over all indices S and all indices I. So whatever branch I take in this family of expressions, I need just to take the max of this. Now we saw 2 weeks ago, max removal. When I have an objective function that contains something that's a max of things, I can get rid of the max by introducing a supplementary variable, epsilon, and adding the constraint that epsilon is larger than all elements of the max here, right? Which is exactly what we do in problem A. Then it means epsilon should be larger than each of those, which gives exactly this. Epsilon is larger than each of those 3 elements for every value of S. So A is the same as P1 here. The difficult thing is really to go in this direction here. Going in this direction is easy if we have a set of formalized steps, which is what I'm trying to give you in this course. And it's important to realize that we're doing this when we do A here. In fact, when we do B, what are we doing? Well, if we look at the original problem, where we're interested not in the worst case penalty, but the integral of the penalties. So the phi is now part of the summation here. Then we can apply the max removal transformation and say that this is a sum of usual terms plus a sum of max. And we've seen that every max we can replace by a supplementary variable, which gives exactly this thing here. Every max here is represented by one variable, and this variable should be larger than this. So do we put one variable for all or one per time step? Well, this leads to different formulation of my objective function. What we have seen here, we can, with a bit more formalism, instead of doing it always on an ad hoc way, we can do it once for all, and that gives this result I'm showing here. If I have to minimize an objective function that is a complicated expression that has sub-expressions here. And I assume that the combination of this is wide sense increasing. That means, for example, it's a plus sign in front. F1, the way that the global expression depends on the first F1 sub-expression is increasing. So I assume this. Then, given this, this is equivalent to replacing sub-expression in the objectives by supplementary variable. I replace F1 of X by epsilon 1, F2 of X by epsilon 2, etc. And I add the constraint that epsilon I is larger than the expression. So I have transferred the complexity from the objective function to constraints here. And the idea, of course, we will apply that when we have max, because we know that being larger than the number of max is being larger than all of the constituent elements. So if the constituent elements are linear, this is a classical method, in fact, the most widespread method for linearizing complex problems that are not linear. So the take-home message is we can replace a sub-expression in the objective function by supplementary optimization variable and one constraint per variable, provided that the dependency of the objective function on the sub-expression is increasing here. Toy example, assume you have this complicated example that comes from one of your sub-problem. So 2 variables, x, y, and I have to minimize this. So we see that the objective function has 3 elements. Here I'm showing three different ways I can break it into constituent elements. What I can say, it is this minus 5x minus 7y. So I say the first element that I zoom on is simply this one here, exponential 2x plus 3y. And the rest is, I don't consider that as sub-expressions. I keep unchanged here. That means I can replace f1 by a first variable that I call epsilon. And I have to add the constraint that epsilon is larger than the expression here, which is given by that. This problem is exactly equivalent to this one. Which one is better? It depends. It depends on what objective you have. You have solvers that are able to solve a number of problems. Very often what we want is to lead to linear problems. But here, what I'm showing is simply the manipulation of problems. Variables, which is not always a good idea. So it's not necessarily what you want to do. Sometimes you may want to do it the other way around, but this is one thing. I consider is not this one, but f1. I consider being an expression. That means I consider that the general form is exponential f1 minus 5x minus 7y. Check that the global expression is increased with respect to the term f1 that I'm using here, which will be here. I replace f1 by some epsilon, use exponential epsilon, where have the constraint now epsilon is larger than 2x plus 3y. So that is an example of equivalent to this problem. This is perhaps tractable because that gives convex optimization function exponential epsilon the convex of epsilon plus linear. The constraints are linear. So when we have convex function with linear constraints, a bit more complicated than linear program, but there are many cases there it's still working well. And if I want to be as complex as possible, I can say, well, each of those terms I consider as an expression. So I consider that the objective function is the sum of three things, and each of those things are my term. So f1 is this thing. So I consider that my objective function is f1 plus f2 plus f3, where f1 is this, f2 is minus 5x, and f3 is minus 7y. So I give this problem, minimize the sum of those three variables. But f1, the first term, epsilon, is larger than or equal to f1, which gives this constraint here. Epsilon larger than exponential 2 blah blah. The second term, which is minus x, so eta should be larger than or equal to minus 5x, which gives this constraint here, and similarly for zeta. So those three problems are equivalent. As you can see, they have different shapes. They can be solvable easily with some solvers, some of them not at all. Question? Of x, correct, but it's subtle here. This is why I wrote here. We have to consider the global expression as a function of the sub-expressions. So the global expression is the sum of three things.
But then f2 is still going to decrease h, no?
Sure, but the theorem doesn't say whether f1 or f2 is decreasing. The theorem says h should be increasing with respect to f1, f2, f3.
H is with the minimalization or without?
H is given here. I can apply this in three different ways. Here is one way of applying. I say h, that's the mapping that transforms the variables, x, y, the sub-expressions into the original objective function. That's the original objective function. I can consider that I have three sub-expressions, the first, the second, and the third. Then my mapping h is equal to f1 plus f2 plus f3. So I consider this to be equal to f2 plus f1 plus f2 plus f3.
Could you give an example where it's decreasing with f?
Well, if I would put Oops. If I would put minus, if I would put H, I write this. So one way to write this, I say it's F1 plus F2 plus F3, which means this is F1, this is F2, and this is F3. This is what I did here. And the question is, when I do this decomposition, is it increasing with F? Does increasing F2 increase the total objective function?
So it's completely independent of what is inside F2.
Exactly, exactly. Because what we're saying is, essentially we're saying, I will replace the function F2 by a variable F2, if you want, or a variable epsilon2. And I would say I want to minimize epsilon2 such that epsilon is larger than F2. Of course, that works if the objective is increasing with respect to the members, because when I minimize epsilon and epsilon is larger, I need this consistency. Well, in fact, let's apply this to this example. I guess that will answer your question. I'll close the poll in a few seconds. Closing. We have a tie on F, and the correct answer is F. So let's look at the solution. Perhaps let's look here. So A, let's look at A. A is saying I replace the variable, the expression absolute value of X by an epsilon1. Okay. And the expression absolute value of Y by an epsilon2. The question is, when I do this, I consider this as X plus 2 F1 minus 3 F2. Is this increasing with respect to F1? Yes, but with F2, no. So this is an incorrect. This is incorrect. Doesn't mean that it's, well, probably it means it's not equivalent. But it's an incorrect application of this. So this is certainly not deriving from what we said. So that's what we discussed here. A is saying I 2 minus 3, and this is not white sense increasing, therefore it's not correct. B, what is B doing? B is saying I replace 2 absolute value of x by epsilon 1 minus 3 absolute value of y by epsilon 2. Now the question is the function that maps epsilon 1, epsilon 2 to this, is it increasing with respect to epsilon 1 and epsilon 2? And the answer is yes, because every member, the first member is increasing with respect to epsilon 1. When we take the max is increasing with respect to each of its arguments. So yes, if we increase epsilon 1, we increase this. Similar if we increase epsilon 2. So then I replace the constraint. I keep all the original constraint by this script x here. And I need to add the constraint that epsilon 1 is larger than the thing that we have removed, which is 2 absolute x and minus 3 absolute y here. So that's the textbook application of this. Now, how about C? Well, C, I'm just applying max removal. I had an objective function that's the max of 2 things, and I replace it by yet another optimization variable, and the constraint that the optimization variable is larger than the 2 members here, so which we obtain here. So C is the ultimate step of the transformation of B. So here is how a problem such as P can be transformed into something that is not yet a linear problem. We have the absolute value, but this we will see later. We have seen the max removal transformation. In fact, we can see that's just an application of what we saw today. So I could have given that from the beginning, but that would have been a bit complicated. Remember, we saw when we had optimization problem where the objective was a sum of components, each component was itself a max. And we know we can replace every component by an optimization variable and adding the constraint that the optimization variable is larger than the expression that we have replaced by. And then we know that t is larger than f is equivalent to t is larger than each of the members f. So the max removal is exactly a special case of what we have seen here. Voila. Time for a break, perhaps. So it is almost 10. So the goal of those little technical drills was to make sure you were able to manipulate them when we have problems and in optimization problems. And 2 messages: max of max is overall max, min of min is overall min. So we've seen that in one example when we're trying to say problem P1 is equivalent to what? Well, this is one of the tricks we use. But max of min is in general different of min of max. Right? So that's the take-home message. If you have max of min and min of max, well, you have a problem, in fact. You should not apply mechanical rules. And in order to get rid of max and min and perhaps also other embarrassing things that we will not discuss in detail in the lab, but you can easily imagine, we've seen some of the examples with the exponential, for example. We can add supplementary variables by replacing every sub-expression in the optimization function by variables and constraints with some conditions that everything is monotonic, varying in the good direction. So that was our technical parenthesis. Now let's come back to our second variant of MPC. So the MPC we have seen is the most widespread and the most useful. Sometimes, in particular, when we do, I would say, smart grid dispatch plan, for example, and we will see an example here in the case of the energy system, we may be interested in what is called scenario-based MPC. So what is that? Well, it's an idea where in order to make it more robust, we assume that we know more than just a point prediction in the future, but also a prediction interval. The problem with scenario is how to find them and how many to find them. When we add scenarios to an MPC, we will increase the number of variables. So very often we do fairly crude things, which is what I did here. I assume that about the temperature, I know a point forecast and amplitude of the forecast, uncertainty bounds. By the way, if you look up the Swiss Meteo app, you will see such amplitudes in the temperature. It doesn't give just a point forecast, but gives a whole band here. So I took this as my input. Now I have more information about my forecast. And the question is, how can I enter that into my MPC framework? Well, it's fairly easy. We do the same as before. So remember, with MPC, we start always by observing the current state. And then we use prediction. Before I had one prediction. Here I have one prediction per scenario. So I have one scenario, which is, for example, the high temperature scenario, another scenario, which is the low temperature scenario, and I consider them as scenarios. So a scenario, there are only three scenarios, not 3 to the power of the number of steps, only three scenarios, a high, an average, and a low scenario. That's a very crude form. Very often, for example, when people apply this to predicting wind variability for wind energy, they have more scenarios than just a high, a low, and a medium. They have scenarios with set point where we say we assume something happens now. And at this point, there are low, middle, and average. And a bit later, again, low, middle, and average. So you can combine this in having more. That will typically, if we have a number of breakpoints, you will have 3 to the power number of breakpoints. But here I assume I have just 3 in total. So I have now 3 families of forecasts. And essentially what I will do is I will solve the MPC, the optimization, the multi-step optimization problem independently, almost independently for every scenario. There are 3 scenarios. I find a sequence of actions, but I don't have 3 independent. It's almost independent. I don't have 3 independent optimization problem because I'm saying for every scenario I compute a sequence of actions with one big constraint here, which is that for the next time step, the first action I take, which is the only one I will implement, I force the constraint that the actions are the same for all scenarios. That's the main trick of scenario-based MPC. So we add one set of action per scenario. If we did not add this constraint, then we would have 3 independent optimization problems. I would compute a set of actions for scenario 1, for scenario 2, for scenario 3, and then I would have 3 actions to implement. And since I don't know which scenario will occur, then I have a problem. So we don't have this problem because we impose this constraint here. Then we need to, as usual, when we have scenarios or uncertainty, we need to manipulate the cost to have something that makes sense. Here we have, like in stochastic optimization versus robust optimization, we have different possibilities. So when we call it robust MPC, it means the global cost is the max over all scenarios of the integral costs. So we don't know which scenario will occur. We say I compute for every scenario a possible trajectory, and I'm prepared for the worst case. When we prepare for the worst case, we call it robust MPC. So when computing the cost with scenario I, we assume that the disturbance follows, of course, the prediction of scenario I. So that makes a problem which is 3 times bigger in numbers of variables than what we had before. We solve it. We obtain a set of actions to be implemented at time t, which are the same for all scenarios, so I can implement them. And then we can do it again. Nature will reveal the true disturbance, which probably will be none of the scenarios and hopefully something in between. And then I do it again. So in terms of this car driving illustration, it is as if saying my scenario corresponds to different assumptions I'm making on the future or what I can observe for the future, which is here the shape of the road. So I'm assuming I have a very number of sensors. I have LIDARs, lasers, radars, cameras. They don't all give exactly the same thing. So I have some uncertainty about how things are. So I have multiple scenarios. And hopefully I will be able to drive given this uncertainty, which means I will, for every scenario, compute a trajectory. If the scenario is the dark blue, that's the trajectory I would have. If the scenario is the light blue, that's the trajectory I would compute. And I impose that my first set point is valid for all scenarios. So here it will be in the intersection of the two here. And that's the one I will implement, which makes sense because we don't know which scenario will occur. So we are ready for everything and we implement just one here. So this is scenario-based optimization. Now let's apply to David's house. Then we have the difference is that in the integral cost, we have one integral cost per scenario. So we add an index or a superscript I for the control actions and for the resulting state. And in this case, we do robust, so we take the max over the three scenarios of those sums here. Now, what are the constraints? Each of the controls actions have their powers, so they have constraint here. There's no ramping power. There might be some for a heat pump, but here it's ignored. We have the state equation, which is one trajectory per scenario. What is important to remember here, which is not is implicit here, is that the optimization variable, capital T, the state starts at time t plus 1. That means the value of the state at time t is assumed to be a fixed known parameter in this optimization problem. So in these equations here, when S is equal to T, for example, the right-hand side here is an input, is the same for all three scenarios. That's the observed value here, whereas all the others are optimization variables here. So we solve this. We add the constraints, as we said, that at time t, which is the first action I will take, that they are all the same for all scenarios. And the disturbance here will depend on the scenario given the. So how can we translate that into something that MATLAB can digest for us? And we need to get rid of this max of sum here. So one way to do it is to apply exactly what we just saw. We can say that this is the first embarrassing thing we want to get rid of is this nonlinear but convex function for the cost here. And I apply what we just saw before the break. This expression I replace by a variable. Now there is one for every S and for every I here. So I replace this complex expression by a variable. While doing that, I must ask myself the question, before replacing, am I sure that the total objective function is increasing with respect to this function? Here the answer is yes, because we have max, sum, and plus. So all are increasing operations here. So I replace this by this function here, and I obtain the equivalent problem where I've added quite a bunch of variables, as many f's as there are i's and s. And I need to add the constraint that fi is larger than this function here. Now, fi, yes, this function. I still have a max here, but we know also, so second step, we need to remove this max by adding another variable, epsilon, and saying that the max is larger than all the terms, which are now itself summations here. So we're almost done. We still have a nonlinear part here, but we know that phi is the max of three expressions. So I can replace this by these three inequalities here, where W is the weight, that is the slope of this penalty function. So this is how my problem, which was highly non-linear before, is transformed into something that is very linear. And that's the correct way of doing it, hopefully. By doing that, I have a principal method that I know exactly which variable to add and why. If I want to be smart, I can even remove the W here, and that simplifies a bit by putting the W in the cost here, which is simply a change, one-to-one change of variables. So that gives us the optimization problem that I need to solve if I solve the robust scenario-based optimization problem. So as you can see, the difficulty of MPC is not in the concept. Once you understand the technique, it's fairly simple. It's very powerful. So sometimes things that are simple are not very powerful. Here, it's very simple and very powerful. Of course, there's a price to pay. You will tend to have optimization problems that have some complexity, and you may need to manipulate them to make them digestible by software, which is what we saw here. So at the end, when we add all the constraints explicitly, this is what we obtain here. We have the state evolution, we have the complete problem. I applied it to the same example as we saw before. So that's what we saw before the break. If I do an MPC that is a standard MPC, if I am a bit paranoid and I want to make it robust, robust means I want to make it work not just for this point prediction, but for anything that would be any of the three scenarios. Well, we see two things. The cost is increased, which now that's the monetary cost that I'm displaying, not the optimal cost as computed by the optimization function, but the monetary cost. We see that the hard constraints are satisfied. So the soft constraints had a weight which was large enough that in practice they became hard constraints. But we see that the operations is a bit different. Here we see that in the robust MPC starts to heat a bit before than the non-robust MPC. Because the robust MPC is ready for the worst case, which would be that the temperature is very low. So given I have a certain power in my heat pump, in order to bring to the max temperature at this point, I need to start earlier if the outside temperature is large. Now, because in fact the realization was close to the average scenario, it was not optimal to be robust, but that's one thing we know. I mean, the more robust you are, the more you are ready to affront some of possible uncertainties, then the more you will pay for that. That's why insurance companies exist. Right? We're willing to pay an insurance premium because we're optimizing in front of uncertainty. So if it would be very important to work well even when the temperature is low, which probably is not the case, because again, the impact if your MPC is working, we see that the temperature was still okay. No, with this realization, the temperature was still okay. So the take-home message is, well, there is a price to pay, where the monetary price will this year. Now, if we assume that the actual realization of the temperature is closer to the lower bound, at least in the first day here, we see we're closer in that period to the lower bound here, then we see that the robust MPC in this case is performing better than the non-robust MPC. So non-robust MPC is optimizing for this temperature. Of course, it's recovering, it's always correcting the error it does, but while correcting, it continues to be a bit in the wrong direction. So it corrects always, but the integral of those corrections have the effect that the cost is slightly larger, which is as expected. Here you were paying an average cost in order to be better in all possible cases. So we see here we're in a case that's closer to the worst case, and then this one pays a small penalty. So if you care very much about this scenario, what will happen here? Here, what is the price to pay? It's not so much in the temperature. It is in the fact that we were not optimal in our use of energy. Here, we are forced to heat when the price is fairly low. We are forced to heat more when the price is not low, which we see here. Here, we heat a bit more than there, which translates into a higher cost there. As for stochastic programming, there are variants of this. You may, instead of taking the worst case cost, you may take what is called the average cost. So this variant of scenario-based MPC with average cost would make sense, in particular, if the constraint is really a very soft constraint. We will typically take the robust with max when we've added soft constraints that we care about. So we make an extremely large price penalty to make it like here. No, not here. Exactly, this formulation here. So what we care is the worst case cost, and in particular, there's the monetary cost, but there's also the penalty here. So we would like that, in some sense, the constraint is satisfied always. If we want this, we would tend to put the max. If the soft constraint is not just for convenience, but is truly soft, which is probably the case for temperature, then an alternative is to optimize the average cost. Now, there is a problem when we want to optimize the average cost, which we have already confronted, when we were confronted with, we need to put probabilities on the scenarios. That's why it's often not done, because putting probabilities on scenarios is considerably more difficult than simply having uncertainty bounds. If you're able to put probabilities, which require more statistical information, for example, if I have my 3 scenarios, worst and middle and average, I can put probabilities of them that give a good approximation of the distribution of temperature. Of course, it's only an approximation. I'm replacing a continuous distribution with a distribution that has only three scenarios. So if I'm able to have this, for example, you would typically find things like a 95% probability for the average and 5% separated into 2 extreme cases. Then I want to minimize the average, which now instead of the max, we have the sum of pi I this. Pi I is known, is fixed and constant, so that simply makes a completely linear problem. At least this part is linear. We still have the phi, which is nonlinear. And using the same technique as before, we add 1 variable for each of the expressions that is here, and that gives us a linear problem. In fact, it's a bit simpler than the other one, but its solution will depend on the values of pi I. I don't show the results of this for the example we had before. They are quasi the same. Now, complexity, there is a price to pay for this. The major price to pay is the number of time steps. So for example, if in the example I showed, with 1 minute time step and receding horizon of 1 day, that gives a number of variables equal to 1,500 close to. So I have to compute state, action, and predict disturbances for 1,500 steps in the future. This still works. Linear programs are able to handle hundreds of thousands of variables, but this is why it's important to be linear here. If it doesn't work, if your problem becomes too large, there is a technique called variable time step to mitigate this problem. Well, the technique consists in saying that we want to zoom in for the very short term, but for the long term, we may not to have such a detailed zoom on all the instances. What is important when I do this storage modeling is to anticipate, for example, that in 5 hours, there will be a period of low price. I need to anticipate this, but whether this period happens in exactly 5 hours or 5 hours and 5 minutes, this inaccuracy may not be very important. I need to anticipate, so I may start charging my battery because I know in 5 hours, approximately something bad will happen. So the idea is to have variable time steps, for example, the time step that you would like ideally for the short term, then larger time steps for the midterm, and even larger time steps for the rest here. So if you apply this technique to this, you obtain the time number of variables 40 instead of 1,400, so a dramatic reduction by almost 2 orders of magnitude here. Voila, so let's terminate with 1 or 2 quiz. What is now a valid formulation for an MPC of David's house? Perhaps given all the flexibility we have in defining max and sum and everything, which, if any of the two, is a valid MPC formulation for David's house, right? For the heating system that we have considered so far. Here, be careful. I'm using some leftover from last week, right? I replace the scenario by these constraints here. I assume at every time S, I have a min and a max band for the temperature, and I impose that it works for every temperature in this range. I close the poll in a few seconds. And the majority says A, but the majority is not always right. Let's look at A. I'm minimizing over the variables, all the U, all the epsilon, and all the T. And here I have robust constraints. This inequality must be true for all value of theta, but it's not possible. I mean, if I have equality for one value of theta, I cannot have equality for a distinct value of theta here. So you can always formulate it like this. Well, you will need to remove the quantifier theta somewhere to make it tractable by MATLAB. And while removing, you will discover that you have a problem. We've seen how to remove it last week. We solve intermediate optimization problems. But here you will quickly discover that it's impossible because we have equality constraints, not inequality constraints. So that is an impossible job, right? Nobody can solve this problem. It's an ill-posed problem. How about this one? This one is well posed because we optimize over theta, and theta satisfies this. So it's a well-posed optimization problem. You can put it into MATLAB, and if the problem is bounded, it will give you a solution. However, when we do this, we have theta in the optimization variables. That means it's equivalent to having the quantifier there exists, theta. So we are here solving the problem of controlling the house, assuming we can also choose the optimal outside temperature. We or someone else can choose it. So we're assuming there is someone outside that is helping us with choosing always the best temperature that will reduce our cost. That's the problem we're solving here, which is probably meaning we take theta S equal theta S max here. That's probably the choice that will give us the less cost. Yes?
Last time we also saw that all disturbance, we could also put it.
Correct. But here there's no for all, right? We just say theta is an optimization variable.
Yeah, but for me, it's kind of the step after we've transformed the for all.
No, that's the step we have when we transform the there exists. When we remove a quantifier there exists, we've seen we can simply remove the quantifier and put the variables into the set of optimization variables. This is what we've done. And from a control theory viewpoint, this means we're assuming we have cooperative operator that is trying to help us with the optimization, which is something we do if we have a dual optimization. If at the same time outside we can manipulate the outside temperature optimally, that's what we would do. But that's probably not what we wanted to do. So this is also not a valid formulation of the many ways we can formulate the problem. In fact, the reason we do the MPCs the way we do it is that exactly it's difficult to add the quantifier other than doing the kind of scenario-based MPC we have discussed here. So now if we want to do it correctly, which one is a valid formulation of the robust MPC for David's house? Back to this question. I close the poll in a few seconds. And the majority says A only, which is the correct answer. A is exactly the problem we've seen with a robust formulation that takes the max cost. That's the integral of the penalty cost over one scenario. We take the max over all scenarios, which is, again, the robust thinking. We have a number of scenarios. We don't know which one will happen, and we don't want to put probabilities on them, so we just take the max. Here, it's a bit different. The max is inside the sum. So that means we have the integral of the worst case cost over all scenarios at every point in time, which could be feasible, but it doesn't correspond to the model we had. Here, we're assuming that at every point in time, we can choose any of the three scenarios, and we can jump from one scenario to the next at every point in time, which means we don't have three scenarios in total, but 3 to the power, the number of steps. At every time step, we could choose the temperature, which is not what we did. This is typically not what we do for such systems. If we have an uncertainty band, then it's very unlikely that the temperature jumps from the very lowest to the largest randomly at every time instant. This is what this would be based on. If we assume this is true, which is probably not the case, this is this here. So here the cost is not achievable by any of the three scenarios we have. It's achievable by a mixture scenario where we don't have three scenarios, but at every time step we can mix any of the three possibilities here. So the cost is inconsistent, in fact, with the rest, because now we have only three trajectories of temperature, but the cost here is assuming this mixture of scenarios. So this is assuming different hypotheses in different parts of the formulation. So it's probably a bad one. This one here, what's the difference here? Well, here we've dropped the last quantity here, with the last constraint in this. So here we're simply assuming we minimize three trajectories for the three scenarios, and we will implement an action that depends on the scenario. But since we need to implement the action before nature reveals its values, this is not acceptable. We need to have this constraint because we will implement this one. And with this thing, we don't know what to implement at time t. We have three solutions, and which one do we implement? We don't know. Voila, so that's the topic for today. So MPC is intellectually very simple. It's based on a cute idea of receding horizon, and it uses optimization to obtain a policy. As you can see, the policy is the value of ut that we obtain. By observing xt, we derive a value ut. But the way we obtain ut is not by saying ut is some linear matrix applied to x plus a constant. No, we solve an entire optimization problem, and that delivers ut. So that's a quite generic formula, which in general is very far from linear. Most solutions of such problems are extremely nonlinear, in fact. So we obtain a nonlinear causal policy, and compared to the control techniques that we have, its major part is that it looks ahead. That's why it's important for systems that have storage and variable conditions in the future. Then we need to know what to store now based, if we manage a storage, we have a storage because this will be used in the future. So we need to look ahead. That's typically going with storage, batteries, thermal systems. It requires predictions, as we have seen, but they can be coarse. Now, in practice, as soon as we have an MPC, we start colliding all the different elements that we have seen that are a bit embarrassing. We have max, mean, integrals, everything. Different ways of combining, depending when we put weights or we want just to put the max. Everything is possible. Everything depends on the information we're ready to buy, or we're ready to put the resources to obtain. So there's a large variety of concrete MPCs, and manipulating them to make them tractable to a standard optimization problem is one of the hurdles that I hope have made it lighter with what we've seen today. We have seen robust MPC, which is used sometimes perhaps we should remember that the MPC by nature is robust in the sense that even if it's based on only one forecast, as soon as it sees that the forecast is different from what it has obtained, it will change and update its state here. So even a non-robust MPC, in some sense, has some robustness. The term robust MPC alludes to the fact that we have multiple scenarios and we constrain the action to be the same for all scenarios. Voila. We're a bit early today. I guess that's unusual, but good news. So that's all for the theory part of today. Now, in this next lab, you will have to apply this and see and be able to appreciate the benefit and the complexity also of those techniques. Don't forget to do the quiz. The quiz is here to help you with checking some of the things we've seen here. Voilà, bonne semaine et bon courage.